Space, vast, endless, and filled with wonders we are only beginning to understand. From the tiniest subatomic particles to the largest galaxy clusters, the universe is a place of mystery, beauty, and unimaginable scale. But what if I told you that everything we see, every planet, every star, every galaxy, accounts for only a small fraction of what actually exists? What if the true nature of our universe is hidden in an unseen realm beyond the grasp of human senses? Today we embark on a journey to uncover the greatest cosmic mystery of all time, the invisible forces shaping our universe, dark matter and dark energy. For centuries, scientists believed they had a good grasp of how the universe worked. Newton's laws explained motion, Einstein's relativity redefined space and time, and quantum mechanics revealed the strange world of subatomic particles. But in the 20th century, astronomers started noticing something strange. Galaxies weren't behaving the way they were supposed to. According to our understanding of gravity, stars at the edges of galaxies should be moving slower than those near the center, just like planets in our solar system. But they weren't. Instead, they were moving just as fast as the stars near the core. Something invisible, was exerting gravitational pull, keeping them in place. Enter dark matter. The term dark doesn't mean evil or ominous. It simply means unknown. We can't see dark matter. We can't touch it. It doesn't emit, absorb, or reflect light. And yet, it must be there, because without it, galaxies would simply fly apart. In the 1970s, astronomer Vera Rubin made one of the most important discoveries in modern astrophysics. She observed the motion of galaxies and confirmed what others had suspected. The gravitational force holding them together was far greater than the visible mass could account for. This was proof that something massive yet invisible was dominating the universe. Scientists estimate that this mysterious form of matter makes up about 27% of the universe. Compare that to normal matter, the stuff we can see like planets and stars, which accounts for just 5%. But here's the catch. We still don't know what dark matter is. Could it be a yet undiscovered particle? A relic from the Big Bang? A completely new form of matter beyond our comprehension? The search for answers continues, and the deeper we dig, the stranger the universe becomes. But dark matter is only half the mystery. If dark matter holds galaxies together, there must be something that's doing the opposite, pushing everything apart. And in 1998, scientists found it, an invisible, unexplained force that is accelerating the expansion of the universe, a force so powerful it defies the very fabric of space-time. They called it dark energy, and it changes everything we thought we knew about the fate of the cosmos. At the turn of the 20th century, scientists believed they had a solid grasp of the universe's structure. They knew that gravity, the force that binds planets, stars, and galaxies together, was the dominant force at play. But in 1998, everything changed. Two independent teams of astronomers, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, set out to measure the rate at which the universe was expanding. At the time, most scientists assumed that gravity was slowly pulling everything back together, that the universe's expansion, set into motion by the Big Bang, was gradually slowing down. So they looked at Type Ia supernovae, dying stars that explode with predictable brightness, like cosmic lighthouses scattered across the universe. By measuring their distance and how their light was stretched, they could determine how fast the universe was expanding in the past compared to today. The results were shocking. Instead of slowing down, the universe was speeding up. The farther away a galaxy was, the faster it was moving away from us. Something was overpowering gravity, some unseen force pushing space apart at an ever-increasing rate. This force became known as dark energy. But what is dark energy? The truth is, we don't know. But there are theories. One possibility is that dark energy is related to something Albert Einstein proposed in 1917, the cosmological constant. At the time, Einstein believed the universe was static, neither expanding nor contracting. To make his equations match this idea, he introduced an invisible repulsive force, a mathematical fudge factor that counteracted gravity and kept the universe stable. Later, when Edwin Hubble discovered that the universe was actually expanding, Einstein dismissed his idea as the greatest blunder of my life. But what if it wasn't a blunder? Today, many scientists believe the cosmological constant might be real. That dark energy could be a fundamental property of space itself, a kind of energy woven into the fabric of the cosmos. There's another theory, one even more bizarre. Some physicists suggest that dark energy isn't just an invisible force, but evidence of a deeper reality. That our universe may be just one bubble in an endless multiverse, each expanding and evolving in its own way. Others believe dark energy could be a new, exotic form of energy, perhaps a quantum field permeating all of space, one that is slowly gaining strength over time. But no matter what it is, dark energy is dominant. Scientists estimate it makes up a staggering 68% of the universe. Combined with dark matter, this means that the stuff we actually see, the stars, planets, and galaxies, makes up less than 5% of everything that exists. Think about that for a moment. Everything we've ever known, everything we've ever observed, is just a tiny sliver of the cosmos. The rest, hidden, unseen, unexplained. And here's the most terrifying part. If dark energy continues to push the universe apart, what happens to the future of everything? Some scientists believe the universe will expand forever, growing colder and darker until all the stars burn out and space becomes a void of lifeless nothingness. Others predict a more dramatic fate, the Big Rip, a scenario where dark energy grows stronger over time, eventually tearing apart galaxies, stars, planets, even atoms themselves. The very fabric of reality ripped apart by the force of cosmic expansion. Could this be the ultimate fate of the universe? Or are we missing something? Some deeper truth waiting to be uncovered? If dark energy is truly pulling the universe apart and dark matter is holding it together, then we are caught in the middle of a cosmic tug-of-war, one that has shaped the universe from the very beginning and will ultimately decide its fate. But how do we even study something we can't see? How do we prove the existence of forces that have no direct interaction with light, no direct presence we can measure? That is the challenge facing modern astrophysics. And to solve it, scientists have turned to some of the most powerful tools ever created. One of the biggest clues to the existence of dark matter comes from a phenomenon called gravitational lensing. Albert Einstein's general theory of relativity predicted that gravity can bend the path of light, just like a lens distorts an image. So when astronomers observe distant galaxies, sometimes they see their light warped and stretched by the presence of something massive in between, a mass far greater than all the visible matter we can account for. This tells us one thing. There is something else there, something invisible, yet incredibly powerful. Another major clue comes from the cosmic microwave background radiation, or CMB, the afterglow of the Big Bang. This faint radiation, first discovered in 1964, is the oldest light in the universe, dating back nearly 13.8 billion years. It's like a fossil, preserving the conditions of the early cosmos. And when we analyze the CMB, we see something strange, patterns that suggest the universe has far more mass than what's visible. This missing mass? Scientists believe it's dark matter. So, what is dark matter made of? There are theories. One possibility is WIMPs, weakly interacting massive particles. If these hypothetical particles exist, they could explain the extra gravitational pull holding galaxies together. Another possibility, axions. These ultralight particles could behave like a strange, ghostly fluid, influencing the universe on a cosmic scale. And then there's an even wilder idea. What if dark matter is not matter at all? Some scientists propose that dark matter might be a fundamental flaw in our understanding of gravity itself, that perhaps our equations need to be modified on large scales. One such theory, called modified Newtonian dynamics, or MOND, suggests that gravity behaves differently in the vast emptiness of space than it does here on Earth. But no matter which theory turns out to be true, one thing is certain: dark matter must be there. It's woven into the very structure of the universe. But what about dark energy? If we can't see it, can't measure it, then how do we know it's real? One of the strongest pieces of evidence comes from the large-scale structure of the universe, the cosmic web. When we map out the locations of galaxies, we see something remarkable. They are not scattered randomly, but instead form a vast, interconnected network of filaments and voids, a cosmic spiderweb stretching for billions of light years. These structures are shaped by dark matter, its gravitational pull guiding the formation of galaxies over cosmic time. But when we look at the way these structures are expanding, we see something shocking. The expansion isn't just happening, it's accelerating. Something is pushing everything apart, something stronger than gravity itself. This is where dark energy comes into play, and as we dig deeper, we realize that dark energy isn't just a passive force. It might hold the key to the ultimate fate of the universe. For billions of years, the battle between gravity and expansion has shaped the cosmos. Dark matter, an unseen glue, holds galaxies together. Dark energy, an invisible force, pulls the universe apart. But what happens next? What does the presence of these forces mean for the ultimate fate of everything we know? To answer this, we must peer into the far future, millions, billions, even trillions of years from now. Astronomers have proposed several possible endings for the universe, each dictated by the delicate balance between dark matter and dark energy. The first scenario is called the Big Freeze. In this future, dark energy continues to dominate, pushing galaxies farther and farther apart. Over billions of years, galaxies will drift so far from each other that their light will no longer be visible. The night sky, once filled with stars, will grow darker, emptier, lonelier. Over time, stars will burn out, one by one. No new stars will form. All that will remain are black holes, silent, consuming, waiting. And even they won't last forever. In time, through a slow process called Hawking radiation, black holes will evaporate into nothing. The universe will become a cold, empty void, a dark, silent abyss. This is the heat death of the universe, a place where nothing happens because nothing can. A reality where time itself may no longer have meaning. Pause. Deep, resonant sound effect. But there is another possibility, one far more violent. What if dark energy doesn't remain constant? What if it grows stronger over time? This leads us to the terrifying scenario known as the Big Rip. If dark energy continues to accelerate the universe's expansion, there may come a point where even gravity can't keep up. First, galaxies will be torn apart. Then solar systems will unravel. Planets will be ripped from their stars. Atoms themselves will be shredded, unable to hold together against the relentless force of expansion. In the final moments, even space-time itself will disintegrate. The very fabric of reality, ripped apart, the universe, once vast and structured, will dissolve into nothingness. And yet, there is one more theory, one that suggests that the end may not be the end at all. What if the universe isn't heading toward a final stillness or destruction, but toward a rebirth? Some physicists believe in the idea of a cyclical universe, a universe that expands, collapses, and is reborn in an endless cycle. This is the theory of the Big Bounce. In this scenario, dark energy might not be eternal. Instead, it could reverse course, causing the expansion of the universe to slow, then stop, then collapse inward. Galaxies would rush toward one another. Matter and energy would compress. The universe, shrinking smaller and smaller, would be squeezed into an unimaginably dense state, just like at the beginning. And then, a new Big Bang, a new universe, a new cycle. Is this how reality works? Will the cosmos fade into nothingness, be ripped apart, or be reborn again and again in an eternal loop? We don't know. But one thing is clear. Dark matter and dark energy are not just invisible forces. They are the architects of our universe, the unseen hands shaping our past, our present, and our future. And the deeper we search for answers, the more we realize. We are only just beginning to understand the true nature of reality. For centuries, humanity has looked to the stars, searching for answers. We have mapped the heavens, charted the motion of planets, and uncovered the fundamental laws of physics that govern reality. Yet the greatest mysteries remain unseen. Dark matter and dark energy, together making up 95% of the universe, continue to elude us. We know they exist, we see their effects, but we don't know what they truly are. And this presents one of the biggest challenges in modern physics. How do we solve a puzzle when we can't even see the pieces? detectors shielded from cosmic radiation, researchers are hoping to catch a glimpse of a WIMP, a weakly interacting massive particle, the leading candidate for dark matter. If found, it would revolutionize physics, proving that the universe is filled with an entirely new form of matter. Meanwhile, powerful telescopes like the James Webb Space Telescope and the upcoming Vera C. Rubin Observatory are scanning the skies, tracing the gravitational influence of dark matter on distant galaxies. And at the world's most advanced particle accelerator, the Large Hadron Collider, scientists are smashing particles together at nearly the speed of light, hoping to create dark matter in a lab for the first time. But what about dark energy? If it is the key to understanding the fate of the universe, how do we study something that seems to be woven into space itself? One possibility is to look deeper into the cosmic microwave background radiation, the afterglow of the Big Bang. Subtle patterns in this radiation could reveal how dark energy evolved over time, giving us clues about whether the expansion of the universe will continue forever or eventually reverse. Another approach involves mapping the large-scale structure of the cosmos, studying how galaxies are distributed across billions of light years. If we can detect shifts in this structure, we may uncover the true nature of dark energy and whether it is constant or changing over time. And there's one more possibility, one that could shake the very foundations of science. What if dark energy isn't a separate force at all? Some physicists believe that dark energy might be an illusion, a sign that our understanding of gravity itself is incomplete. If this is true, then solving the mystery of dark energy might require rewriting the very laws of physics. We stand at the edge of discovery, facing the unknown. For the first time in history, we have the tools, the technology, and the knowledge to peer deeper into the cosmos than ever before. What we find in the coming decades may redefine everything we thought we knew. Will we uncover the true nature of dark matter? Will we decode the force that drives the universe apart? Or will we stumble upon even greater mysteries, revealing a universe far stranger than we ever imagined? One thing is certain, the story of dark matter and dark energy is far from over. And as long as we continue to look to the stars, to ask the impossible questions, and to push the limits of human knowledge, the universe will continue to reveal its secrets, one discovery at a time.